do it, but I got to do it. I got to do this to get started. So today we want to talk about chapter 4, and I don't believe we got into chapter 4 at all uh, in our previous work, and want to get going on chapter 4 and maybe into chapter 5. Chapter 4 and chapter 5 are, we're not going to teach the whole chapter. It's not worth it. Some of this stuff you get in other courses, and it's just not, we just don't have time to go deeply into chapter 4 and 5. Okay. So why is this chapter important? They mentioned in this section right here, I've got to get you onto the right screen. Um, the invention of the transistor and the integrated circuit and all the other stuff that they did up here. So anyway, that's kind of important, I guess, to an extent. And then we get down into linear dependent sources and analysis of circuits with dependent sources. And we're going to skip the rest of the op-amp part because we really don't need it. And we're only going to work problems 1, 2, and then 5. And that's all you're going to be assigned. So basically, we'll work those 3. So chapter 4 assignment is 1, 2, and 5, those 3 problems in chapter 4. And I didn't get published yet, but chapter 3, the problems were 3, 4, 9, 11, 20, 41, 58, and 61. So if you didn't, I haven't put that on the website yet, and I will, but those are due as well. Now, in this chapter, on chapter 4, we're just going to look at these devices. These are the devices that we really need to look at, all right? So what are these? These are dependent sources. This is dependent on this, this is dependent on this, this is dependent on this, and this is dependent on this, all right? Notice that 2 of them are current and 2 of them are voltage on the output, and 2 of them are current on the input, but they switch. So here's a current to voltage, voltage to voltage, current to current, voltage to current. So you can have any of those 4. All right, so those are dependent, and those are the symbols for it. It's a diamond. So all you have to do, and this is not hard, is you find the current or the voltage in this circuit at this point in time, and then you do the multiplication and you output the other out over here, and that's all you do. It's not a hard it's not a hard thing to do, and that's why we kind of don't stress it very much. But on the other hand, we need to. Why is this important? Because these are the models that many of the times we talk about with transistors. Now, we use transistors in a little different way. We don't use these models, but many times, do you know why? What's the difference between electrical engineering and engineering technology? One of the biggies is right here, because with electrical engineering, you have to model it. You have to model it and make an approximation that is exact. In engineering technology, we look at a transistor circuit and we say, this is this times this. In other words, the resistance at the base is beta something or another, and I forget, it's been a while since I've taught 2010, but in 2010, that we did an approximation. That approximation, you're not allowed to do in electrical engineering. You got to do this, all right? Does that make sense? You have to have everything defined down to the last little bit. You can't do an approximation. Now, when you get to the real world, you do approximations all the time. But here, this is what electrical engineers do to model a transistor. That makes sense? So we're not saying that we're better or we're worse or whatever. This is just a different approach at the idea of a transistor. But this is one of the models for a transistor. And you're not going to have to memorize this because I'm not going to ask you to do that. But this is how this works. You get a voltage over here, you multiply it, and then you get your voltage out over here. Okay? Now you can combine this circuit with this circuit by putting a resistor in here. In the middle of this chapter, they do an analysis of that, and I'm not going to ask you to do that. Okay? You can do that if you want to, and it's not a bad thing to do, but you don't have to. Now you can put these into circuits that have everything combined, or you can have them as two separate circuits. This does not touch this over here. This part over here and this part over here don't affect each other except for this little piece right here. Okay, so that's that. Now let's get down to actually looking at some of these and saying, now what do you do here? Well, how would you do this problem? Good question. You'd find the current down through here based on I source. Now notice that they don't ask you for I source. They don't give you a value for I source. Now sometimes they do, sometimes they don't. Make sure that you look at this and say, there is no I source, therefore this doesn't work. No, what are they looking for here? The ratio of VO over IS. Because as IS changes, VO changes. Okay? So what would this be a model of? Of output voltage, it's a MOS device. Metal oxide salt, MOS or CMOS device. So typically, when you're amplifying voltage, when your output is voltage, you're talking about a CMOS device. When your output is current, when you're amplifying current, it's a bipolar device. NPN, PNP bipolar device. Okay, so that's what this is talking about. So if your question, what on earth are we talking about here? That's exactly what we're talking about. But now the question is, how do you solve it? Well, they don't give you a value for IS. They ask you to get the ratio of V out over IS. Because as IS wiggles, V out wiggles. So you're amplifying a circuit here. You're actually amplifying it. That's all this is. Okay, so how do you do this? Well, you find Ix, which is that value right there. Use current divider. I hate current divider, but on the other hand, you can use it if it's two devices. How do you do current divider? Well, it's the opposite. It is the opposite over the sum, and there it is. Okay, what is the opposite of this guy? It's this guy. So what is it? 50 over 25 plus 50 times IS, and there you go. That makes sense? There's your IX. There's your IX. Now you multiply that by what? 48. Now you're going to try to find out what the output is across here. Now how do you do that? I out is 300. It's this. It's I out is this over here, right? It's so you do it again. It's a minus sign. There's a minus sign involved. I out is IY. Here's IY. So you want to find I out. I out is opposite over the sum, and then that gives you I out. Okay, I out is right there. Now, V out is this. So there's my final answer. So my final answer, V out, is minus 6,000 IS. Any questions? There's my power out. Wow. A lot of difference in power, isn't it? Hey, any questions about that? You can see where this is going. This is not hard. It's the same thing we've done before, but now you've got to do this extra little step, and that's all this is. Okay, so that gets you that one. Now this is another one, and it is, here's my input, and then here is my I, and then here is my voltage supply. Okay, and this is voltage. So how do you do this one? Same sum, second verse. Find I, multiply it by, multiply it by R, and that gives me my voltage supply, and then you do voltage divider to get my RL. That's it. That's all you got to do. This hard? Nope, it's not hard. All right, so that's the answer to that one. Now we get into this guy right here. And I'm going to skip this guy right here because it goes through and it looks at and gives you all this stuff. And it's nice, it's kind of nice, but we don't need this. You don't really need this, and there's the equation for it. And I'm not going to try to explain it, and I'm not going to try to tell you that you need to know this in order to survive in general. But if you do want this, put this in, there's the explanation for it. All right? Again, we're not trying to impress you with derivation of formulas, but this is the formula. And then when they ask you at the end of the chapter, they basically just ask you to solve this formula, plug and chug, and that's it. So I'm not going to ask you that. There it is again. You can see it right there. All right, there it is. So that's the same thing. There it is. Here's the first circuit. Here's the second circuit. It's a model of a transistor. Okay, so let's go down to the end of the chapter. And now they talk about op amps and a lot of things with op amps and multisim, et cetera, et cetera, et cetera. But typically, I just want you to be able to work a problem on paper, and then I'm not too interested in the now the op amp circuits you get in 2020, right? Anybody who's taken 2020, you've got op amps all over the place in 2020, so you really don't need to do it again here. So I'm going to skip them. But if you have not had op amps, you may want to look at this. But this is a little different explanation for op amps. I should probably go back and do this page by page because that's how we want to portray this. And I'll go back up here and so I'm not going to go through this real fast, but I'm just going to scan through this so you can at least, okay, so there's example 4.2. There's my RB, or my forward resistor, the one that the bridge one. And I'll go through this so you can at least look at it. So right now we're just scanning through the rest of chapter 4. Okay. Okay, moving along. Morning, we're scanning through chapter 4. If you want to know why the big silence, it's just we're going through the rest of chapter 4. If you want to read it through it, you can. Here it is. Now, they can do mesh analysis with dependent sources, and that's the way it typically would be solved if you have combined circuits. I would use mesh analysis. This would be the approach that I would use. Um, and you notice what he did here in the middle. What did he do? He changed this into a this. Did everybody follow that? See the sneakiness of this guy? I mean, who would have thought of doing that, right? But there it is. So you can do that. What is this? Norton. What is this? Thevenin. How do you get from here to here? Use your Thevenin to or Norton to Thevenin rules. There you go. Then you can do this. And there's your mesh analysis for that circuit. We're just going to go through 3 problems in this chapter. 1, 2, and 5 is what we're going to do. Call it a day. Okay. So amplifiers. Thevenin equivalent with dependent sources. Um, okay, so here we go. This is a caveat to Thevenin. To find the Thevenin equivalent of an active circuit, we must leave the independent sources on or else supply excitation from an external test source. This means that the Thevenin resistance cannot be found by the look-back method because that method requires all independent sources to be turned off. Turning off the independent sources deactivates the dependent sources as well and can result in profound change in the input and output characteristics of an active circuit. Thus, there are 2 ways of finding active circuit Thevenin equivalents. I'm not going to ask you to do this, by the way, in a test. Thank you, Professor Evans. But this is how it's done. We can either find the open circuit voltage and the short circuit current of the interface are directly involved, or directly solve for the interface IV relationship. Okay, so this is how you do this. Okay, so I have a dependent source with the independent source turned off, IN equal IS equals 0. The resistance seen at the input is RE. Since the dependent current source is an active and acts like an open circuit. Applying Kirchhoff's current law at the node A with the input source turned on yields this. By Ohm's law, the input voltage is this, therefore the input resistance is this. Okay, that's how you find R Thevenin. Again, I don't expect you, we've gone so far with Thevenin, and all of a sudden we throw this caveat in there, we say, with dependent sources, you can't just use the look-back route. In other words, looking back from the right to the left. You can't do that. You have to do this. All that being said, you never will ever remember this, and you probably will never use this, except for the fact that there it is. Okay? Not going to be on a test. Not going to have to worry about it, except for the fact that there it is. Okay. Here's another one. I want you to understand that I'm in the same boat as you are. I don't want to have to go back and justify this either, because this is a technicality with Thevenin that we just kind of ignore, and we say it doesn't exist, but it does. So here we go, and this is how it's done. This in chat, if anybody ever asks you about independent or dependent sources, you'd say independent sources, it's okay. Dependent sources, it's not okay. So the dependent, when they say you're dependent on something in the Thevenin part of it, you just can't automatically use your old rules, okay? But here's how it's done. Again, not going to ask you this on a test. I'm not going to hold you responsible for this, but this is something that you might actually be asked about someday. Well, you use Thevenin for everything. What about a dependent source? Smart alike, but that's exactly what they're saying, that you can't always use it. Here's when you can. Okay, now they're intent on getting you involved with transistor models, and there's one for the NPN transistor. Right there it is. There's your good old NPN. EET 2010, right there. And moving on. The op amp part of this is right here. Here's your ideal op amp. The non-inverting formula. And someplace the inverting one. So what are op amps really good for? A lot of things. You can do a lot of circuits with them. As a matter of fact, when I first started teaching, they actually had, and they still may have in some places, an analog computer. What are analog computers? A bunch of op amps with various things attached to the front end of them. Okay, so you can put a capacitor in front of them. You can get an integral. You can put a derivative. You can put an inductor and get it. You can put capacitors in and get derivatives, integrals. You can do all kinds of stuff with them. You can do all kinds of formulas analysis with them. And why are they useful? Because they're very high frequency. You can use these for very high frequency applications that you can't do with computers, okay? And then certain types of communications. But this is a review of op amps. If you're interested in them, you have a video now of how they work. Okay. Onward we go. I just did a bookmark. I didn't know what that was, and that's all it is. I need to get rid of it. Okay, we'll get to the problems eventually. It's a long chapter. You notice we're moving through a lot of pages. Okay. I went to a class one time where the guy, at the end of every important thing, he'd say, okay. And I think I just picked that up. I have no idea why I say that, but okay. Terrible. So this is taking a little bit of time. But if you want to read through this and see if anything of interest, here it is. I'm going to buy the book. Here it is. Has anybody bought the book? How much?
I got Amazon for $78.
78? Not bad. Anybody else for edition 10th edition? Well, you know why I'm doing this, so I don't need to explain myself. I'm not trying to cheapen this down at all, but on the other hand, if there's something here that is of interest to you, you can stop and gaze at your leisure, and then we go on. Okay. This is not a pretty way to do it, but I guess it's the only way I know how to do it. I just have to keep on going. Sorry it's taking so long. You want to listen to the lady as we're talking? Did I play the lady for you the other day? Yeah.
It was terrible.
It is. It's worse than me. I mean, that's pretty bad, right? With 4 courses, and 2 of them, I've not. I teach 1020, and I've taught it more than once, and I've got a book that I've gone through, and I'm pretty comfortable with that one. But this one, I'm not comfortable with. This is the first time I've gone through this myself. I've gone through this course with another book, the Staley book, or the Stanley book. And I got pretty good at that one. But the first time you go through something, you're just learning it yourself. And I'm sitting there last night, falling asleep, waking up, falling asleep, waking up, 9 o'clock at night, and I say, what is important about this? Well, not much. But you do understand that you do need to look at that first part of this course, of this chapter, and at least understand it. And I didn't realize how long it would take to scan all this stuff in, so now we're just kind of, if you want me to stop anywhere, I'll stop. But you realize this will be on the web in about 24 hours, and you can look at it yourself. Okay. All right. So these are op-amp circuits, and a lot of the things you can do with them are very, 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 very powerful. Summary, now we're down to the problems. Okay, problem number 1. Now, I've not worked these ahead of time, so if you find me making a mistake, stop me, yell at me, whatever. But we're going to work through 1, 2, and 5. Maybe, I don't know, 3 or 4. 3 and 4 use that resistor, and I'm not going to do that one. Okay. So number 1, and what are they asking for? They're asking for the gain V out over V source. So basically here you have to do, so number 1, Vs plus to minus, and then you've got 200 up here, and you've got 300 down here, and then you've got a separate circuit over here, and this is Ix, and little I means it's a time-varying signal. So you're looking at a ratio. Basically, this is an AC circuit. This is going to wiggle. This is going to vary. And then over here you've got a diamond, which is a dependent source, and it's a minus to a plus, and Rix. Then you got 500, and then you've got 2K, and you got V out. So what is Ix in terms of V and in terms of Vs? Vs over 500, right? And then this voltage supply is what? R times Ix. So what is the current? What is the current IO? IO is equal to R times Vs over 500. It's a minus because it's going this way. and then you've got R times IX, which is this. That's my IO. And then V out is equal to 2,000. No, IO is, this is my V divided by, the whole thing divided by what? 2,500? Okay, is that right? And my V out is 2,000 times I0, or 2,000, 2K times, bless you, minus R V supply over 500 times 2,500. Is that right? Cancel. Okay, so V out or V source is that number. Isn't that right? Because the current here would go this way. It's opposite of IO. So it would be IO is a minus the voltage, the current going in this it's IO is minus R minus R times IX, then divided by 2,500. Okay, this would be my V divided by 2,500, and this would be the numerator. The denominator is the denominator, so it would be you'd just basically move this up to here to 25. Everybody agree with that? Is that right? Any questions about this one? V out over V supply is 2 divided by 5, and then that's 2,500, so it's 5 times 2,500 or whatever that is, and then 2/5, okay, it's 2/5 of minus R over 2,500. That's it. Any questions? Easy? Yeah, straightforward. Any questions about that one? Let's go to the next one. I'm getting no looks at all. Like, did I make a mistake, or do you agree with me? You like it? Okay, it's what it should be. Not necessarily the kind of problems you want to get, but these are the kind of problems that this chapter has. Next chapter is kind of the same. These two chapters just kind of but on the other hand, we need to at least understand a little bit about what these symbols mean and how these work, and the warning about Thevenin and Norton, which is in this chapter. So I think it's important that you understand that there are caveats to Thevenin and Norton, and there they are. Okay, so this one is a little different. This one they want I out over IS. So here is my IS. And can I do the honors of changing this to a voltage supply instead of a current supply? Now, what would be the voltage supply? It'd be IS times 100, right? And then that would be plus to minus. Everybody see what I'm doing? And then I'm going to put my 100 up here. Why can I do that? Make it easier, right? And then I've got my 200 over here. That's my I. Well, it is V over R, right? V is 100 IS. So my I1 is equal to 100 IS divided by 300, or IS over 3. Over here, we say, what is my I out? And here, I'm not going to flip it because I've got half of my current here is going to go this way, half of it's going to go this way. And it's the negative. So basically, here, my output is equal to my IO is equal to half, because these are equal, of 100 I1. I is 100 I1 divided by 2, and it's got a negative sign in front of it because it's going in the opposite direction. Now, V out is IO times 2,000. So V out is equal to I0 times 2,000, or minus 100 I1 over 2 times 2,000. Okay? And what is I1? It's I source. I source divided by 3, this whole thing divided by 2 times 2,000. End up with that, and V out over I source is equal to minus 50 over 3 times 2,000, or whatever that is. End of story. Not hard, very doable. There it is. Any question? Oh, they want V out over V1. V out over V1 is what? They want V out over V1 instead of I1. What is V1? It's I1 times 100. This times 100. Okay. So it's 100. So basically, you just put the 100 up. You divide both sides by 100. So basically what you do is V out over V1 is equal to minus 50 over 3 times 2,000 divided by 100. You're done. That's it. I'm not too interested in these problems, but the fact is they're there, all right? And you need to know how to do them. 5 is the same, except now, what do we have? What are we doing with this? What is this? How do you do this? How would you do this circuit right here? 5. There's 2 of them. How do you do this? Use mesh. If all else fails, use mesh. So you got 5 volts, plus to minus. You got 1K. Mesh is the hammer you can use just about any time, and it'll give you an answer, okay? 1K here. Then we've got a dependent source, 200 IE, which is this right here. And then we've got, over here, we've got 1K. All right. So what is this? IE is equal to I1 minus I2. So now we can write this, minus 5 plus I1 times 1K plus I1 minus I2 times 1K equals 0. This gets a little bit more tacky, okay? Now here we've got I2 minus I1 quantity times 1K. And here we don't know what the voltage is. We do this. Well, anybody got any ideas? Because I don't know the voltage across there, do I? I can't write it because I don't know the voltage. If it were voltage, I could. Okay, right. Dang on it. Well, I'm gonna have to look at this one myself and figure it out because if you come up with an answer for this one, good. If you can't, I thought I could just write these. I looked at them last night. I thought, yeah, they're not too bad. But this one's a not easy one. And oh, I know. Ted. Again, bad call. 4.5, use node analysis. Okay? Now, with that in mind, this is my circuit, plus to minus 5 volts. Okay? 1K, 1K. And then this little guy right here, which is a mess, 200 IE. That's current supply. Then we go 1K down here. Now, it isn't so bad except for the fact that now they call this as VA, all right? Now we use node analysis. So what is coming in from the left? 5 minus VA over 1K. Now that's the current coming in from the left. What's the current going out the bottom? Okay, and what's the current coming in from the right? Plus 200 IE, all right? What is going out? So this is coming in, this is coming in. What is going out? VA over 1K, all right? What is IE? It's equal to VA over 1K. So now we can substitute in here VA over 1K, and I've got it. 5 minus VA over 1K plus 200 VA over 1K equals VA over 1K. What is VA? I don't know. Sort and sift, done. Everybody see that? You see, I couldn't use mesh, but then I went to my other brother, and there it is. That's what this does. Did everybody see how that's done? I use node and mesh analysis as equal partners, and sometimes one gets it, sometimes the other gets it. Usually 9 times out of 10, mesh will get it. That's why I went to mesh first, even though I knew it last night that no, this is a node analysis problem. Now, I rewrote it and I got it because I can use current. So you use whatever is available. You take advantage of whatever they give you. And in this case, it's node. All right? Any questions? What is VA? I don't know. I'm not going to worry about it. You figure it out. You hand it in, and that's that one. Okay, now what about the second one? How are you going to solve the second one? Well, it worked so good for the first one, I think I'm going to try it again for the second one, and it does. You do the same thing for the second one. Okay? Once you've found VA, what do you need? What else do you need? Well, from that you can solve everything else. If they ask you for something else, you got it. But this is what cracks this problem open, using nodal analysis and VA. Any questions about that? Squeezed out of that one, right? I knew this one was nodal analysis all along. I was just kidding you. No, I didn't. Always use mesh first. When it doesn't work, then you fall back to other methods, and that's what that's about. Okay, so that's it. 3 problems. I'm moving on. Okay, chapter 5. Chapter 5 is not hard either, but it's just one of those things where, why did they ever come up with this? Well, as an engineer, you need to express everything in some mathematical form. In other words, you have to be able to mathematically describe everything, okay? And if the signal is not a steady state signal, then you're in trouble. So basically, you have to come up with something. So what do? You invent something, and they did. They invented this U thing and all of that kind of stuff. But it's, you know, this is one where I'm going to say it. I had to go through this, so do you. Does that make sense? That's exactly, I could describe this and say, we'll never have a problem like this. We'll never do this. You see, never. Yep, we'll have to do it. But occasionally, excuse me, they do. I got to go back and undo this. Go back to chapter 5. They do this by chapters. Okay, now chapter 5 is this part of it. So again, in other words, this is something that's been around forever. But you have to define things, and that's what they're doing. They're defining a step form, an exponential, and a sinusoidal, and all these kind of composite forms. But basically, we kind of tail off after the step form. Okay, the step waveform is kind of the one that we all hang our hat on, and after that, we say, "Yep, I can do that too. Yep, I can do that too. I can do that too." But anyway, the sinusoidal waveform is another one we kind of talk about. But you've already done this one. Just a matter of, we'll get through it. Okay, this one you've already done a lot in 1020. This one you have done a little bit in 1010, but except for the fact that we just kind of skip over it. Okay, so how do you define a signal? That's basically what this is about. How do you find that signal as opposed to if it starts at 0? How do you find something like this? How do you find something like this? How do you find something like that? And by the way, if you have a signal that's coming in like this, and you actually, your input, or let's put it this way. If you have a signal that's coming in like this, but you have an input that's only detecting pulses like this, will it work? The answer is, on your computer or on your PLC, the answer is sometimes. You do not depend on this working for this, or vice versa. Bad news, sometimes they work, sometimes they don't. And I've had it go both ways. So how do you fix that? Times a diode. Go ahead.
I don't know. I take it back.
Huh?
I was gonna say maybe you could amplify your square wave so that the bottom of it is at 0, but I don't know if that's it.
It is. Yeah, that's an answer. Yeah. You can move everything up, yeah, you can move everything up. That's an answer. Yeah. How would you do that? How would you do that? Use an op amp. Yeah. Everybody understand the question and understand the answer? Sometimes you don't get there easily. You cannot assume that because this is a pulse and this is a pulse, that if your input says it's a pulse input, it's going to work. Duh. Sometimes it comes around and bites you. Sometimes it works. Sometimes it's the NP thing. Sometimes it's just, it doesn't work because it's not ready. It's not set up for that. And you have to do whatever. And that's why they pay you money. And that's why you took 1010 or 2010 and 2020. Because all of a sudden you're being asked to do things with signals that are not nice, okay? They're not nice. All right. So on the other hand, is it good to design a little circuit board and hang it in a control panel and advertise the fact that you did that? Why not? Because every problem that exists in that whole control panel they focus on that because they don't know how it works. And they'll say, what is that? That's the problem. Even though it may not have anything to do with the problem, the maintenance people don't understand it, they don't like it. And if you can solve the problem with a standard piece of equipment, if it's a red lion or somebody's counter or whatever, if you can solve it with a physical device that's got plastic around it, and it looks like it's been manufactured by a manufacturer, they'll accept it 20 times over your little breadboard. I'm serious. So if you can, stay away from breadboards. If you can't, accept the consequences. Because they are. I've done it, and everybody, there's the problem. No, it's not. Yes, it is. Oh my goodness. We go around and around and around, and then eventually, if you can, you figure out a way around it. But they're going to blame that part of it forever. I was always a little bit ahead of my time with regard to how I design systems. In other words, I like to be able to do things as efficiently as possible with layers if possible. In other words, if the left one will get you, the right one will. In other words, if you're looking for a signal and this one, it doesn't happen here, it happens here, and one or the other will get it. If this fails, I've got it over here. I've always liked that approach. Sometimes you can't do that approach, but if you can, you do. But anyway, the last system I designed at Owens Corning was one of those that the guy that inherited the system after me, he was an engineer, he could not understand and would never accept. And part of it because he didn't like me as an individual, part of it was because he just didn't understand RS-232. Because I put everything in with cables between different panels using an RS-232 cable. And that was before Ethernet, but it worked, and it worked well. But he couldn't, if anybody took any of those cables apart, the whole thing fell apart. He couldn't understand you can't see it. So, it's just like, oh my goodness. But you can see RS-232 on an oscilloscope, by the way. You can see it being transmitted. You can see it, a little burst, and then it comes back down. Enough on that. So here they are. This would be, what would you say about this? How would you describe this signal as opposed to a signal that starts at 0? Okay, so you write it as what? U of t minus something, okay? So that's what you do. You say U of t minus whatever. So now you've got a signal okay, so you write it as U of t minus something. You write it, can I get rid of this? All right, Ted, get rid of that. So you write it as U of t, something times a voltage times U of t. If you say minus some number, that means that is the time offset, okay? So the U of t by itself means at t equals 0, we go to that value. So U of t means, and this would be the value of 1. U of t means 1. So you go to 1 at t equals 0. All right? So at t equals 0, we go to the value of 1. So if I write 10 U of t, we have a signal that up until 0, it is nothing, but at t equals 0, it goes to the value 10. Okay? Make sense? Piece of cake, right? What if I write U of 10 minus 10? Okay? Okay, let's say 20 U of t minus 10. Okay, so here it is at some value, and here is my 0 point, t equals 0, and this is minus 20 seconds. At t equals minus 20 seconds, I turned that on. Why would we ever pick at minus 20 as a signal? I don't know, but you can. Why would we pick these at all? Because we can then say, what? How would you write this signal right here? It's U of t minus 1. It's 3 U of t minus 1 minus what? See the game we're playing? Here we go with the real world, okay? Here is u of t minus 3u of t. Okay, so this would be 3u of t. And this side is minus, the left side is plus, so I wrote that wrong. This is t minus 1. So here, this would be minus 1, and this would be minus 3u of t minus 5, or excuse me, minus 3, Ted. Okay, so what you do is you subtract off a signal that does the same thing in the exact opposite way, and then you've built this signal. So you build, this is 3u of t minus 1 minus 3u of t minus 3. To the left, it's plus on the time. To the right, it's minus. Okay, how would you write this signal? It goes to 10, so you would say 10 u of t plus 2, and then here you would subtract what? Minus 12 u of t plus minus 2 plus 2u of t minus 4. That's that signal right there. You see the game? At minus 2, we say t plus 2. At plus 2, we say t minus 2. So it's a plus to the left, it's a minus to the right, and then we say 10, we go up 10, and then we stay at 10 until we go to plus 2, and then we subtract 12. And then at 4, we add 2, and we're done. That's all it is. This is how you define that mathematically. You say, can you do this in a mathematical formula? Not really, but this is how you would write it. If you were writing it for an engineering paper, this is how you would write it. This is how engineers talk. So you need to learn the lingo, is all it is. Okay? Instead of just drawing this, you can say it this way. Any questions about that? Do you see this? You see this one developing into a test question? Yes. Oh yeah, these are good test questions. These are excellent test questions. Believe me, they're easy, they're a piece of cake, but yet, if you were not sitting here or studying this, or at least absorbing this, they're totally oblivious, okay? Any questions? Yes? Oh, I'm sorry, I saw that as a minus 2, it's minus 15, yeah, you're right. Yeah, I'm sorry, minus 5, you got it. I saw that, yeah, you're right, minus 15. Very good. Plus 5, sorry about that, there you go. I didn't see that. Okay, now, what else can I do? The impulse function. What is the impulse function? If I take the derivative of a step function, what do I get? Like that. It's called the Dirac delta. It's the delta function. Why they call it Dirac delta, I have no clue, but they do. It's called the Dirac delta. If I took the integral of this function, what would I get? This is the derivative of that function. This is the derivative of that function. What would be the integral of that function? The ramp function. Okay? Now, do we ever get these in real world? Yes, you do. It's called an electric fence, among other things. You design an electric fence, what does it do? It puts out a very high voltage with no pop, with no current to it, very short period of time. Shocks the heck out of a cow, shocks the heck out of you if you ever tag into one. That's how it's, you know, they'll level a cow. Won't kill them, but they'll back off. So if you want to design a circuit like that, there you go. Very high, very quick, done. What is this used for? Slow boy, but it's the integral. This is the integral function of that. Okay, and that's a ramping function. Interesting, but that's exactly what it is. So in so doing, we've now defined two other signals. What is this signal? This is called the Dirac delta. And it is really very, 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 very high spike is what it boils down to. It's called, that's what that's called. It's just a spike. How high does it go? How high do you want it to go? How quick is it? Pretty darn quick. But again, if you were to take the derivative of this signal right here, here's your Dirac delta. This would be a spike going up. This would be a spike going down. Okay? And here, is a ramp function. This is the t function. This is called the t u of t, okay? So the ramping function is this guy right here. So if this is my function, this would be the ramping of it, and then it would level off. So how would I define this function? I define it as, okay, this would be my function, this would be my 3r minus 1, and then it stops, and this is 3 minus 3r t minus 3. So basically I define it as this and this. How would I define the derivative function? As this and this. Write an expression using ramp functions to describe the waveform shown in this figure. Okay, so here is my original signal. Okay, so here's the signal. Here's an expression using ramp function to describe the waveform shown. So we say R, which is my rate of incline, t minus t plus 1. Instead of U, it's R. Okay. I've never used that before, but that's how you describe it. R, t plus 1, which is, it starts up there, minus 2. In other words, if you have a value, now you've got to kill off this one, and you've got to kill off, if you just kill it off, if you said minus 1r, you just make it flat at that point in time. But otherwise, but if you do two of them, actually they're going down, and at this point in time, plus r minus 3. Okay. Does everybody understand? This is the description of that. Okay. Now, I haven't come up with any problems at the end of the chapter yet, but this is kind of where we end this. We don't go into all the other stuff that, you know, how do we define this? Well, you can define this, and you can, but basically, I have not looked at the problems at the end of chapter 5, but this is as far as we're going to go with this. I'm not going to worry about the exponential waveform. If you can get this one, you can get any of them. And I'm not going to worry about defining this one, defining all the rest of them. You get the U1 and the rate and the direct delta, you're done. You don't need to go through all the rest of them. You can look at these, and I will go through them. I'll review chapter 5 here, and I'll give you some problems. I'll put them on your I'll put them on the website. You can start looking at them. There's only 3 problems in chapter 4, and they're very few. We got to get through chapter 6, I think, which is the AC circuits, and we're going to have to spend some time on that before we have our first test. We're not going to get into integrals, or we're not going to get into Laplace. And by the way, if you're taking 4450 from me, it's the same course. Once we get into Laplace, it's the same course. It's not exactly the same course, but it is close. 4450, we do Laplace but here we have to go through, and we use mesh analysis to actually write the equations to get the equations that you use to analyze, which we do much more in this course than we do in 4450. But it's the same basic analysis using Laplace. It's the same course. The exact same techniques are used in both courses. All right, as you can tell right now, I'm just reviewing the rest of chapter 5. I get you a couple of problems, not a lot, but a couple of problems into chapter 5, and we go on. You say, when are you going to end this mad dash when we get to chapter on Laplace? And then we slow down tremendously, because we have to get that, and maybe you have never taken that. Maybe you're taking it already. Maybe you've taken it twice. You get it 3 times from this university. You get it in 3020, ENG 3020, EET 3250, and EET 4450. All get the same thing. Learn how to take differential equations and solve them using Laplace transforms. It's one of the most powerful techniques that you can use to solve to solve differential equations. But we solve them using electrical terms, I and V, and we write equations based on what we've learned up till now, which is mesh and loop, mesh and nodal analysis. So what you've learned up till now is pivotal if you do not know mesh and nodal analysis to being able to do Laplace transforms. All you add is the S variable. That's it. But you got to solve them. You got to do partial. You got to do separation of variables, and all that stuff. Composite waveforms. You can add them together. Yes, you can. There you go. There's a signal that doesn't vary. The frequency doesn't vary. There's one that comes up that does vary frequency, and it does have a special emphasis because it is it's used in electronic signaling devices to detect objects. You vary the frequency, and you get a varying you get varying signals coming back, and some things you detect with low frequency, some things you detect with high frequency, but if you use them both in the same signal, you get a variety of answers, which gives you a better look at something than just if you have one frequency. Okay. And I think I skipped it. So now we're down to the problems at the end of chapter 5. And these are the problems I'm just going to assign to you. They're not they're not bad, but there won't be many of them. And I think I end about 5.6 or 5.7. Yeah, we don't go past 5.7. And I don't know how many of them I'm going to assign to you, but we're going to assign up to you. A couple, three of them, maybe four of them in that range. I'm going to go back and again tell you that you can look at them. Okay, so first of all is sketching. It's a pretty sketchy class in this. Then you write the functions. Then you sketch. And sketch some more. And sketch some more. And I don't think I'm going to do second derivative. Those first derivative, yeah, but second derivative, I don't. We'll see. Anyway. We'll work through these together in class on Monday of next week. Right? I do not know how many of those, I'm not going to assign very many. And that's this chapter in a nutshell. And you got it, and we're going to keep marching on. I've got your homework from chapter 2, and get through this real quick. You can go. You may go. I'm going to go through the rest of these problems just to have them on the video. And I've got your homework there if you want to pick it up. I gave some of it out already, and you're free to go. This is the one with the varying signal right there. So they use different waveforms. Okay. Have a good weekend. Have a good rest of the week. Take care.